So today we'll talk about compressed sensing. Okay, so the idea of compressed sensing is the following. We have, first I'll describe it mathematically, right? We have a vector x in n dimensions. Think of n as very, very large, right? But we know that this vector is S sparse. Okay, meaning that it only has S non-zero components, right? At most, S non-zero entries. Okay, and we naturally think of S as much, much smaller than N, right? And we observe it through linear measurements, right? So we observe it through measurements of the type y equals ax, but A is a short fat matrix representing an undetermined system. Okay, so let me draw here a picture of y equals a, right, x. Okay, so this is the picture to have in mind, where A is an M by N matrix. And we would like, right, the interesting setting is when M is smaller than N, right? And also bigger than S. Will be clear why it needs to be bigger, or at least bigger or equal than S. Right, so this is an undetermined system, right, underdetermined. Right, meaning that we know A, right, because this is sort of our measuring device, right? You can think, I mean, as we saw the last lecture, right, you can think of this as having linear measurements, right, where if I have here the entry y1, right, y1 will be equal to a1 transpose x, right? The number y1 is a linear measurement of x. Okay, so now the question, the goal, right? So the goal is recover, right? The goal is to recover x from y. And of course, an a, right? Because a we know, right? A's can be designed, for example. Right, so of course, in general, we can't do this, right? If M is smaller than N, of course, the linear system is not determined, right? It's an undetermined system, and so we cannot do this in general, but we'll have to somehow use the sparsity, right? The whole point of compressed sensing is to exploit sparsity to be able to solve this linear system, right? And now we can ask all sorts of interesting mathematical questions, right? Given an N and an M, how much sparsity can we handle, and what are good matrices for this, and so on and so forth. Right, so now we already know that for a Gaussian matrix, because we already computed, right, the Gaussian width for sparse vectors, and we know that at least to make this sort of a unique, to make this not only unique but somewhat stable, right? We would like, if A is a Gaussian matrix, we would like to keep the distance between it to every S sparse vector. So then we already know that, with maybe taking M, right? So Gordon's theorem from last time, right? Gordon's theorem says that the number of measurements we need should roughly be the Gaussian width of the set of all differences of S sparse vectors, right? Because those are the vectors that we want to keep the norm, because that way we're keeping the distance between S sparse vectors, right? And so we call this S of 2S, right? And we saw what this was up to constants. This was 2S. I mean, up to constants, the 2 doesn't matter, but let me still write it here, log of n over S, or over 2S. Right, but up to constants, this is just S log n over S. Okay, so Gordon's theorem tells us that we expect to be able to do this for M potentially much, much smaller than N. Right, M can be potentially as small as, right, this potentially is possible for an M that looks something like S log n over S. Right, so think about this. So of course we're going to need at least S measurements, because even if I told you where were the non-zero entries of X, you would still need to measure them, right? You would still need to solve the linear system, right? Even if you knew it was here, here, and here, you would still need to solve the linear system correspond to these columns, right? So you need this linear system at least to be determined. So for sure, M needs to be bigger or equal than S. And basically what we're saying is that, you know, in order to actually be able to recover without knowing the support, you just pay a logarithmic factor. Right? This is sort of incredible, right? And this is what's at the heart of compressed sensing. Because this means that if you have a signal that you know is sparse, and they're everywhere, I'll talk a little bit about them in a bit, then we actually can measure it sort of using only its intrinsic dimension in a way, right? Something that's very close to actually the number of non-zero entries, right? So vectors that are known to be sparse include, for example, natural images. So natural images are known to be sparse in the wavelet bases. So what does this mean? This means that if I take a picture and I save the value of every pixel, if I change to the wavelet bases, then there's going to be zeros everywhere, or things that are essentially zero and I can ignore them. So this means that imagine there's only, you know, there's many pixels. Maybe you have a 10 megapixel camera, it takes many pixels, but maybe say only, let's say, just for the sake of example, 1,000 pixels are 1,000 values, coefficients in the wavelet transform are non-zero. And then one way that you could store the image more cheaply is, well, you just ignore all, transform it to the wavelet basis, take those 1,000 coefficients, record those, record which coefficients they correspond to, and you're done, right? And this completely captures the image. And this should occupy a lot less space in the computer, and indeed it does, and this is exactly what JPEG 2000, for example, does, I mean, for the most part. And in many other images, like you expect MRI scans, for example, to be sparse in certain bases, or astronomical images, and so on and so forth, right? They're sort of everywhere. What this is saying is that, you know, this whole process of taking the picture and then changing to the wavelet bases, and then with the wavelet base, you know, in the wavelet bases, figure out which are the coefficients, drop off the other ones, and so on. This says you don't even have to measure everything to start with, right? If you have a good sensing matrix A, you can even measure just right away almost only the number of non-zero coefficients with this multiplicative logarithmic factor. Right? But up to that, you're measuring roughly the number of coefficients you're going to keep and not the number of total coefficients of the ambient dimension. Right? I mean, this could be many orders of magnitude bigger. Right? And so this will be the, right? This is key. This is the heart of compressed sensing. And there's even a so-called 1 pixel camera, which is based on this idea. This has helped develop faster MRI machines by exploiting exactly this, so that the MRI machine needs to spend less time imaging, say, a person or a patient. Okay? And now what, so here we're already, I mean, we haven't yet proven anything, and we haven't yet even argued that, you know, compressed sensing actually works. We just used Gordon to see more or less what should be the ballpark of the number of measurements that we need. Okay, so now what we'll see is we'll make all this a bit more precise, and we try to understand what it is that we need out of the sensing matrix in order for recovery to be possible. Okay, so let me keep this here. So one very popular property is the so-called restricted isometry property. Right? It's very similar to the idea from Gordon. The idea is that we want our matrix, our sensing matrix, to be an isometry on sparse vectors, because if it keeps the norm of sparse vectors, right, in particular if it keeps the norm of 2s sparse vectors, then it will keep the distances between s sparse vectors, and then it's sort of, you know, it's at least two images that are a little bit different. Their measurements are also a little bit different. This is very stable, very quantifiable. This is a good, will be a good surrogate for when it is that it's possible. And then we'll actually use this property and similar ones. One can use it to prove that that recovery is possible. Okay, so this is one of the most popular definition in related to compressed sensing. So this is the restricted isometry property. right? Also known as RIP. Okay, and so it goes as follows, right? So we say a matrix A, an M by N. I'm here not putting reals because it doesn't really matter if it's reals or complex matrix. Satisfies the S delta RP if it says isometry on all S sparse vectors up to an error of delta, right? So if for all vectors X S sparse, we have that the norm of A X squared smaller or equal than 1 plus delta X squared 1 minus delta. Right, so this is one property that's right, that's very, very popular when looking at compressed sensing. Right, so we say that a good sensing matrix, you know, if a matrix satisfies this, it definitely at least feels like a good sensing matrix, right? Because S sparse vectors keep the norm. Of course, if you want to measure S sparse vectors, you need the RIP property for 2S, so that then you keep the distance between this way you'll keep the distance between every 2S sparse vectors, because you will keep the, right, you're keeping the norm of the difference. Right, just that we saw in the other lectures. Right, and in particular, this is just like Gordon. Right, it's exactly the same thing as Gordon. The only difference is that we do the things with squares. Right, before we had that with hyperability. If I take A to be Gaussian or G to be Gaussian, we had something like norm of G smaller or equal than 1 plus epsilon x. Right, 1 minus epsilon x. We just have to take the square, right? If we take the square, we have just, you know, delta here gets replaced by 2 epsilon plus epsilon square, and here it gets replaced, right? The delta here becomes 2 epsilon minus epsilon square, right? So we can just, right? So we can just use Gordon and substitute with the, you know, instead of for delta, we just pick the epsilon that gives the right delta, and this will give us immediately a matrix. It will give us that a matrix with Gaussian entry satisfies the restriction isometry property. So here, since, you know, since the smaller the delta, the stronger the property is, we could even just take delta to be, say, 3 epsilon, right? Because epsilon is between 0 and 1, so epsilon squared is always smaller than epsilon. So we can just take, for example, delta to be 3 epsilon. Okay? And so what immediately we get from Gordon is that if we get a theorem that's you know, sort of one of the central theorems in compressed sensing. I mean, I'm still yet to prove that the RP property implies anything, but once we get there, this will be a very central theorem. This follows immediately from Gordon, right? Then if I take a matrix A, right, with Gaussian entries, with n 0, 1 entries, IID entries, right? It's an M by N matrix. Right? Then if I take, right, then 1 over AM, right? I need to normalize the matrix, right? 1 AMA satisfies the, say, delta 1/3. Sorry, I pick delta to say 1/3, right? So I could just pick the epsilon to be say 1/9. Right, satisfies the S 1/3 RIP. Okay, let me rephrase this in another way. Right, then, right, if the number of measurements is much bigger, right, is bigger or equal than a constant times S log n over s, right? This is the Gaussian width squared of the sparse vectors. Then d if then 1 over a satisfies the s 1/3 RIP. Okay, so if we take a Gaussian matrix, Gordon's theorem immediately gives us that it satisfies the restricted isometric property. Okay, and here I pick a third just for no good reason. It'll be that this will be enough to imply recovery, right? But you basically need a constant. I don't remember now what is the optimal constant. Maybe it's like a fourth, but a third is maybe it's like around 0.4, but a third is smaller than that, and so that's enough. Okay, so immediately this gives us a way of building RIP matrices where M is just, maybe I'll want this show up in big here, right? There exists a universal constant C such that if M is bigger or equal than C S log n over S, then this random matrix satisfies the restricted isometric property. Okay, this is sort of a central statement in compressed sensing. And what we're going to see, or what one can show, we'll prove this in a slightly different way, so we won't actually directly prove this. But one can prove that if a matrix satisfies the 2s 1/3 RIP, then it actually works for sparse recovery. Not only, right, it's clear that it separates all sparse vectors because it keeps the norm of all 2s sparse vectors, right? And so the difference between a couple of s sparse vectors is a 2s sparse vector, but actually it allows for recovery with an efficient algorithm, as we will see. Right? But the amazing thing is that now, this is a random matrix. So, when you build a machine, you probably don't want to build a machine with random things, right? You wouldn't put the random Gaussian coefficients on your machine. And also, we know this happens with high probability, right? These are all statements of with high probability, right? With probability going to 1 as all the dimensions and so on go to infinity. But now there's a question: what if I want to deterministically construct, right? What about deterministic matrices A? Okay, so for random ones with random Gaussian entries, for random ones, I can get S to go all the way. Okay, we can ignore this n over S. Let's just take this to be n. So even doing a little worse, right? We take S all the way to something like, right, like M over some log of n, right? But now I'm built, right? If I think of how big the sparsity can be, right? Once my matrix is set. However, if I want to do deterministic, turns out the best that it's known. I'll talk a bit about this in the next lecture. Turns out that it's easy to get to m half over, say, some. Okay, let's not worry too much about maybe some polynomials of logs of n. That part is not so important. I can just take m to be of the order of n. Maybe m is a small constant times n, right? And so it turns out that going past square root of m, which is way, way smaller than m, seems very, very difficult. And there is indeed one success that goes to 1/2 plus a little epsilon, which I'm not even sure in which digit. I think is like 0.000, and it has a bunch of digits. I don't even remember how many. Right? And this is a very sophisticated construction, and we don't know. So even if I ask, what about getting S to be something like m to the 0.6 over polylog with deterministic constructions? And we have no idea. This is, I think, a fascinating open problem. Okay, but we'll talk a little bit more about how to get this is known as the so-called, this is the so-called square root bottleneck, and we'll talk a little bit about how to get square root m, because we'll have some interesting connections with frame theory. Okay, but how do we actually recover? Let's say that the matrix satisfies their IP and so on, but how do we actually do recovery? Right, let's say A satisfies their IP, right? So in particular, there's no other, they cannot be, right? There's no way that there's another sparse vector which would also be, right, there cannot be any other vector z that's sparse such that a z also equals to y, right? Because otherwise x and z would be sent to the same place, so x minus z would be sent to 0, and a two sparse vector cannot be sent to 0 if the matrix is RIP on two sparse vectors, right? So at least the solution is unique, but now I can ask, how do I actually recover? How do we recover x? Okay. So what would be the natural thing? The natural thing, of course, would be to say, well, I'm just going to minimize the sparsity, right? I'm just going to find the element with the least amount of non-zero entries, such that a z equals y. Right? This would be this is what we call L0 optimization, right? This would be a very natural thing to try, right? Unfortunately, this is hard to optimize, right? This is an NP-hard problem in general. All right, and so we cannot hope to solve this problem in general, right? It's hard like maximum cut and some of these other problems, right? So instead, what we do is we take a convex relaxation of it in a certain sense, not quite in the same sense as we did for things like community action and stochastic block model or max cut and so on, but we're going to consider another norm. Right? We're going to not do a convex relaxation in the sense of changing the search space, but we're going to do a convex relaxation in the sense of switching the norm that we're minimizing, right? Which is not really a norm, but let's say, right? The function we're minimizing by sort of a convex surrogate of it. And so what we're going to do is we minimize the one norm, right? And this is the whole, right? Probably you've heard of L1 optimization and L1 optimization for sparse recovery. And this is the whole idea. Right, what is the one norm? The one norm is just the sum of the absolute values. Right, the vector in an entry is just sums the absolute values. Okay, why is this a convex relaxation? Well, there's a picture that that one can draw that shows that this is illustrates why this is a good convex surrogate. First of all, this is convex, right? So that's easy to see that this is a convex function, the norm, and so in particular, I mean, as all norms are, and in particular right. So in particular, what this means is that this is easy to solve, right? This is something that's a convex problem. Well, maybe I'll argue this a bit in a second, but we'll see that this is easy to solve. Right, but the real question is, why is it a good surrogate and why will it tend to find sparse vectors? And the nice picture is the following. Take, say, R2. The problem is that these things work is in really high dimensions and I can't really draw more than 2 dimensions. But take something, right? Take the sparse vectors in 2 dimensions are just, the vectors in the axis. So let's set them to be like, at L2 norm 1. Right, and let's look at the null space of AX equals Y. Right, so of course here you will intersect in 2 places, right? If you thought in 3 dimensions, you wouldn't intersect this one here. Maybe imagine in that we're in 3 dimensions and this doesn't actually intersect, right? This just goes next to it on the side, right? So now, you know, this is the point we're looking for, right? We're looking for the sparse point, and what is minimizing a certain norm? Well, you can think of it as take the ball of a certain radius in this norm, right? Say take all the points with norm epsilon, and then grow this epsilon, right? What is the ball, the L1 ball? The L1 ball is this diamond, right? These are the sets of points that all have the same L1 norm, right? That's easy to see. And we have the same object, right? This one like this. And now we can imagine, right? This is the AX equals B equals Y. And now you can imagine the L1 ball, someone blowing on the L1 ball and growing. The minimum, right? You know, the place where it's the L1 norm is minimum, subject to subject to this constraint is exactly as we blow this ball, the place where it will touch first. And we'll touch exactly there. Right? So, and if you think about this picture, we'll have a tendency to touch first in sparse vectors because the L1 ball is sort of kinks there, right? Is pointing these places. If I looked at the L2 ball, right? The L2 ball wouldn't do that, right? The L2 ball would have, you know, would be like this and eventually would touch here, right? The L2 ball is not pointy, right? It's just a normal sphere, but the L1 ball is pointy in the sparse directions. And that's sort of, I mean, that's one geometric way of seeing why we expect this to have sparse solutions. Okay, so now in order to convince you that it's actually a good idea to do that, right, I need to convince you of a couple of things. One is that this is easy to solve. I sort of said that, but I didn't really, you know, didn't really explain why. And two, why does it actually give sparse vectors? Right, so I gave you a bit of intuition on both, right? Why it gives you sparse vectors, I sort of give you this picture, and we'll actually prove it next. On next lecture, we'll start proving that indeed this gives sparse vectors, and this will be a solution to that inverse problem. But we'll now address the problem as, can you actually solve this L1, right? Is this easy to solve? Okay. And it turns out it is. Okay, in particular, this is a linear program. Right, so how do we see that? So let's take Z and let's write Z as W plus minus W minus, where this is the positive part and this is the negative part. Okay, so what we need out of these vectors is that W plus and W minus, they need to be always bigger or equal than 0. Right, and for all entry I, you can't both have a positive part and a negative part, right? Either Wi plus is 0 or Wi minus is 0, right? They can't both be non-zero. Okay, but if you have that property, then for each entry, if Z is positive, you just put it here. If Z is negative, you just put it there. Right, and if you have that, then the L1 norm of Z, right, is very easy to compute. It's simply the sum of the entries, right? Instead of being, right, the sum of the absolute values, the absolute value, right, the absolute value of Zi is just equal Wi plus Wi minus, right? Because there's a positive part shows up here, if there's a negative plus, if there's a negative part, it shows up here, right? So this is just, you know, I can write it in this way: 1 transpose W plus 1 transpose W minus. Right, this just adds up the entries in W plus and adds plus all the entries in W minus. Okay, so now if you think about it, right, the L1 minimization problem is simply, you're simply minimizing 1 transpose W plus W minus subject to right? Z is equal to W plus minus W minus. So we have A of W plus minus W minus equals to Y. W plus is bigger or equal than 0. W minus is bigger or equal than 0. And we have this weird constraint, right? That either one is 0 or the other is 0. But I claim that this constraint is not needed, right? Why is that? Because let's say that both of them were 0 at the same time. Let's say there would be one entry where both of them were positive. If both of them were positive, they would be getting nothing from here. If I push them both down, if I take epsilon on both of them, right, this wouldn't be affected. If both of them are positive, this wouldn't be affected either. However, the objective would decrease, right? So there can be no optimal solution to this where both, when one of the coefficients, both W plus and W minus are positive, right? Otherwise, you would just push them down a little and get a better solution. So this is sort of, this one comes for free, and then this is completely equivalent to that, and this is what's called a linear program, right? So this is, right? This is a linear program, right? The objective on W plus and W minus, right? The objective is linear, this constraint is linear, and this inequality is also linear. And indeed, this is efficiently solvable, right? And there's even, you don't need to use a linear programming solver. There's better ways of solving this, but in particular, the fact that it's a linear program immediately implies that this can be done in polynomial time, right? So there are efficient algorithms for this, right? Remember semi-definite program from with our discussions on mixed cut and community detection and so on. This is like a semi-definite program without, positive semi-definite constraints, right? It's even simpler than a semi-definite program. Okay, and so what we're going to do in the next lecture is we're actually going to show that L1 minimization is going to work provided that A satisfies certain properties, and then we're going to show that random A's tend to satisfy these properties. And we're going to do this in a few different ways. There's a few different strategies to show that the optimum of this is actually the original X, provided A satisfies certain properties. We're going to do it in a couple of different ways. Okay, thank you.